Hi, my name is Sagib Naim, and today I'll talk about polynomial neurofields for Subband decomposition and manipulation. And so what is a neurofield? A neurofield is a neural network that takes spatial coordinates and outputs the value of a signal at those coordinates. Recent work have shown that neurofields can represent a variety of signals, showing that such representations are compact, allowing sampling at arbitrary resolution, memory efficient, and can also represent signals with high fidelity. They are also easy to optimize and can handle irregular sample data well. Neurofields have shown remarkable success in a variety of applications, such as image fitting, 3D reconstruction, and novel view synthesis. However, current methods treat neurofields as a black box, meaning that one can only obtain information about a neurofield by querying it with spatial coordinates. This hinders many potential applications of neurofields. First, it is difficult to enforce a known constraint of a signal. For example, if we know that a signal should be band limited by the Nyquist rate to avoid aliasing, representing it with a black box neurofield makes it difficult to enforce the upper band limit. Second, it is difficult to decompose a signal into a set of manipulable components. For example, an image can be decomposed into its low-frequency structure and high-frequency texture. With black box neurofields, such decomposition is difficult to achieve. And so in this work, we attempt to open the black box of neurofields by proposing neurofields that are an ensemble of different networks. Each network is guaranteed to output signals that represent the component of interest. For example, we can design one branch of the network to output high-frequency signal and the other to output low-frequency one. Lastly, each branch can be manipulated in isolation. Our network takes as input spatial coordinates x. Next, x is passed through a basis encoding that consists of a range of functions of interest. For instance, those could be functions of a particular frequency band. Next, the encoded input passes through a number of polynomial layers composed on top of each other. Since composition of polynomials is still a polynomial, this allows us to analyze the output of each layer recursively. Let's look more closely at a polynomial layer. Given two inputs f1 of x and f2 of x, the output of the polynomial layer either applies a multiplication or addition using learned weights w. We prove that if the inputs are within a certain subband, then we can compute the subband of the output of the polynomial layer using the input subbands. This means we can provide provable guarantees ensuring the output of the polynomial neurofields contains certain properties. For example, if we restrict each branch to output a signal of a certain frequency of a different bandwidth, we can decompose the signal into components of different frequency bandwidths. Polynomial neurofields offer a flexible and expressive architectural design that subsumes many of the previous works. Given those advances, PNF still retains the merits of neurofields, being expressive and compact. The left bar chart shows that PNF can reach state-of-the-art performance in the task of image fitting. The right bar chart shows that PNF achieves so with very few number of parameters. Here is a qualitative example comparing NeurIPS results between PNF and the prior work Bacon. PNF is able to produce better novel view synthesis results. In addition to being compact and expressive, we also observe that PNF is able to converge in few number of iterations. On the right, we show a visual comparison for 3D fitting of a thigh statue with 20,000 steps. As we can see, our results capture much more of the details. Here we show the ability to manipulate a neurofield for texture transfer using a set of texture transfer losses. By only manipulating layers that correspond to a particular frequency band, one can control the resulting frequency of the output. Here is another example where we use text to derive the texture. To summarize, we offer a novel class of neurofields called polynomial neurofields, with which we open the black box of neurofields. Specifically, we offer the ability to enforce constraints as well as decompose signals into manipulable and decomposable components. We offer a flexible and expressive architectural design with provable guarantees on the output decomposition. Thank you.